Welcome back. And furthering our exploration of carboxylic acids, we see trichloroacetic acid. I looked it up. pKa is close to 0, which makes it roughly a strong acid. So maybe on our next test, instead of using sulfuric acid as a catalyst or toluene sulfonic acid, we could throw a little trichloroacetic acid in there, and it would do exactly what those other acids do. We're going to finish up chapter 17. Yeah, it's a short chapter. We're going to get it done in one day with a discussion of physical properties of carboxylic acids. And boiling points are one thing, and solubility another thing. These are both very important things. Even though formic acid is a small molecule, it has a relatively high boiling point. Why? Well, when it's pure, formic acid does something like this. I know this is butanoic acid, but the idea is the same. It hydrogen bonds with two molecules behaving pretty much like one. Remember, these are not real bonds. They're extreme dipole-dipole interactions called hydrogen bonds, which is misleading. But the forces are substantial with carboxylic acids. And water solubility, remember the guidelines I taught you for alcohols, where you counted the number of carbons and did a ratio of carbons to OHs. And if it was less than 4-to-1, like 3-to-1, we had miscible liquids, which means liquid dissolved in liquid is miscible. Solid dissolved in liquid, solid dissolved in liquid is called soluble. These are all solids. That's why I don't have boiling points for them. But in the chapter 10 guideline, I told you when it hit 4 carbons, then that was like a cutoff. If it was branched, it would be water soluble. If it was unbranched, then it would not be water soluble. For some reason, the guideline has changed here. The guideline for carboxylic acids, if it's got 4 or less, it's miscible or soluble. And the reason why 4 is more soluble here than with like an alcohol is because there's more extensive hydrogen bonding here. Not only can the OH hydrogen bond with water, such as butanol would do. In fact, I could do the butanol here with my snipping tool. And new snip. Butanol would be just this portion here. Hydrogen bonding with water. I'll get rid of that pi bond. And that's butanol when I get my eraser going. 1 butanol. It doesn't have a carbonyl here to hydrogen bond, so its solubility is almost 0. And just since we're on a review kick right here, tert butanol can't get as close to each other. The tails keep bumping into each other. So H2O can sneak in. That's not a mechanism, that's water sneaking in there because there's a gap between the branched carbons. So soluble and not soluble. Oh, we already have its name. Okay. Once you get to 5 carbons, though, it's a little dicey. That number is pretty close to 0. Hexanoic acids, even lower. Benzoic acid's in the same ballpark. That's 7 carbons in there if you're counting. And what about oxalic? It's a ratio of 2 to 2. OHs, there's 2. Malonic, succinic, oh my, such good. In fact, all of our oh my, such good apple pies would fit here because the ratio is going to be less than 5 to 1. Even when you get to sweet as sugar, the ratio is still less than 5 to 1. Citric acid has not only 3 carboxylic acids, but an alcohol, so not surprisingly very soluble in water. And these I added from previous chapter because they have a similar molecular weight to butanoic acid. And with 5 carbons to 1 ratio, we're not expecting solubility. An amine is soluble. It's because it can hydrogen bond quite a bit. And ketones, not so much. Not polar enough. So that is about all I wanted to say about physical properties of alcohols. And that brings to a conclusion our chapter. Very short segment here. Maybe we should do a question to summarize this. Put these boiling points in order. I like it. Put these in order of increasing BP. Lowest first. Okay. All right. Let's throw an amine in there. Okay. It's too big. I'm going to have the mass almost the same for everything. Good enough. And what are we going to do? Just a slight variation on that one. Good. And we'll throw in that one. And boiling points. We need 5 for a good question, don't we? Yeah. Let's see. How about an amine? There we go. Okay. So, anybody got a favorite first? I've got a favorite. I'm zooming in on the 2 carboxylic acids because we learned to have very high boiling points. All of these molecules have 7 heavy atoms. When I say heavy atoms, I mean carbon, nitrogen, oxygen in these examples. If they're not 7, they're close. So I'm zooming in on molecules 2 and 3, and there's a reason why I'm putting 2 at the very end and 3 before that. And of course, you have to explain. That's where more of the points are anyway. Explain. Oh, yeah, purple's nice. Oh, yeah. Let you know it's more important, huh? All right, so if I have to explain these 2 as a group, I'm going to use the fact they have extensive hydrogen bonding. Now, No, I just gave back my Orgo 1 exams, and a lot of them, hey, they saw in the answer key I was using short forms. But they didn't remember that on this answer key, I also explained my short forms. Yeah, I'm going to use it more than once, so let's have a short form for it. Although I've written it twice to get the, I don't know. Is there another hydrogen bonder in there? Yes, but not one. There's an N in there, but there's no H attached. But there's a hydrogen bonder here. Oh yeah, I'm going to compare 3 and 2 later. V. There's H bonding. I can just go HB. I've explained it. HBO. Just plug out to the movie network. Okay. What else we got? We have this thing which is non-polar. I know a carbon-nitrogen bond is slightly polar, but there's 3 of them. They almost cancel each other. So I'm over here. I'm just going to say 1 non-polar. London only. It's the only time I'm going to use that short form, so let's not have a short form. And then we have a carbonyl, which has what kind of a bond here? With a slightly positive and a slightly negative, because the electronegativity difference is greater than 0.5. It's called dipole. Yeah, we always have to review our intermolecular forces. And then these 2 molecules here, same mass, same functional groups. That's the only time you look at branching. Branching in 3. Lowers intermolecular forces. Why? Because the molecules can't get as close to each other. That's why. So this would be a complete answer in what would be, what, a 6-point question at least. And that brings to a conclusion today's lecture. And I bid you well until Wednesday, and see you then.